Hi, and welcome back. So far we've talked about the structure of ionic compounds, how we form ions from either electronegative or electropositive elements, remembering that metals form cations and nonmetals form anions. And you've seen me use different terminology as we've talked about these, like naming them sodium chloride, magnesium chloride, and that kind of thing. Now we're going to actually have a look at that in a bit more detail and look at how we go about deriving the formulas of these compounds, naming them, and then getting the symbols and the balancing right so that we know that the name that we give them refers to the right chemical formula. So when we talk about the empirical formula of salts, what we're talking about is the chemical formula of ionic compounds. Chemists always refer to ionic compounds as salts. So where we say salt and mean table salt that we use for flavoring our food, when chemists talk about salts, they're talking about any ionic compound. Okay, so this could be aluminium fluoride, copper nitride, magnesium chloride, calcium carbonate. If it's an ionic compound, we can refer to it as a salt. Okay, so ionic compounds are formed between cations and anions. This combination gives us a compound known as salts. The ionic compound formed will always be neutral. So the total positive charge on the cations has to equal the total negative charge on the anions. We give this minimum ratio of cations to anions the name the empirical formula. So the empirical formula is the smallest whole number ratio of cation to anion when the charges are balanced. If you have a look at these examples here with aluminium fluoride, AlF3, aluminium is in group 13, so has a positive 3 charge when it forms a cation. Fluorine is in group 17, so has a -1 charge when it forms an anion. I will need 3 lots of -1 to give me a total of 3 negative charges to balance out the 3 positive charges of the aluminium. So this means that the formula for aluminium fluoride, which will be a neutral ionic compound, will be AlF3. In the case of copper nitride, Cu3N2, I can see that copper has a +2 charge in each of these, indicated by the Roman numeral given after its name. So I have 3 lots of +2, which is a total of 6 positive charges, and 2 lots of -3, because nitrogen is in group 15. So when it forms an anion, it forms -3 anions. So that 2 lots of -3 gives me a total of 6 negative. So 6 positive plus 6 negative is going to give me neutral overall. So I can see I have 3 coppers indicated by the subscript here and 2 nitrogens. When we write the formula for the ionic compound, you can see that we don't include the electrovalency or charges on the cations and the anions. As chemists, we're expected to be able to work that out. We don't write it in the formula. So when we write empirical formulae, they're always expressed in terms of their whole number ratio. So the cation is always written first and given its symbol. We don't use subscripts if the number of the ion is 1. Okay, so 1 is always implied. The charges on the ions are not included in the formula, and the subscripts show the number of each type of ion. So in this case, we can see we've got 1 magnesium, which would be Mg2+, by the way, and then we have 2 chlorides. Okay, we can see here that that +2 is going to cancel out the -2 here, so we would write this formula as MgCl2, and that is magnesium chloride. The cation is always written before the anion, and the net charge must equal 0. One way that you may have seen for writing ionic formulae is called the swap and drop method. So if we first identify the ions that will be going into the compound, so in this case, if we're going to do aluminium bonded to oxygen, we can go to aluminium, look up the periodic table, see that it would be in group 13. Aluminium has 3 valence electrons, so it will want to lose those valence electrons. So I will have Al3+. I'm bonding this with oxygen. Oxygen is in group 16, so wants to gain 2 electrons to complete its octet. Its charge will be 2- when it forms an anion. Once I've identified the electrovalency of the ions that will be in my compound, I can do what we call swap and drop. I take the value of the digit that is on my electrovalency of the cation, and I drop it down and make it the subscript on my anion. I take the value of the electrovalency on my anion and I make that the subscript on my cation. So that 2 will come down and become Al2, and then the 3 will come down and be O3. I'm still essentially cancelling out the charges because 2 lots of 3+ is going to be 6+ that I have here. 3 lots of 2- is going to be 6-, so overall it will equal 0. The math always works if we use swap and drop. The catch is if I have a 2 and a 2. So if I looked at something like magnesium, which is +2, oxide, which is -2, and I swap and drop here, I would get Mg2O2, and that's not right because you remember the empirical formula is the lowest whole number ratio. So instead of this 2 is to 2 is the same as 1 is to 1. So if they are the same number, I can simplify it down to just MgO. When we come to naming ionic compounds, just as with the formula, the cation goes first. They all have 2-word names. The first word is always the cation and the second is the anion. So if we look at these are known as binary naming, okay, when we look at an ionic compound. You identify your cation and your anion, then put the names together to get the name of the compound. So in this case, the name of the cation is sodium and the name of the anion is chloride. I bring those together and I get sodium chloride. Magnesium hydroxide. So I've got magnesium hydroxide as my name. In order to be able to do this, though, we need to know how we name our cations and our anions. So we always have the cation name plus the anion name will give us the compound name. What we need to make careful attention of is the structure of the name. So if it ends in IDE, it's going to be an anion. And then with the cation name, it's always just the name of the element. But pay attention if there's a Roman numeral, because the Roman numeral tells us the electrovalency of that element. And it will generally be used for something that can have a changeable electrovalency, so one of our transition metals. Main block elements, so our S and P block elements. Okay, for cations of the elements, the main group of the periodic table, it's just the name of the element. So the cation of sodium is also called sodium. Okay, we just refer to it as the sodium ion. Things are a little different if we look at cations and elements that have more than one charge state, though, such as the transition metals. In this case, when dealing with transition metals, we must always specify, and we specify by a Roman numeral. So because iron can exist as a +2 or +3 cation with its electrovalency, what we do is we specify which one we're talking about. So if we're talking about the Fe3+ ion, we would call it iron 3, and we put that Roman numeral in black brackets, and that tells us which electrovalency we're talking about when we name the cation. When we name the anion, things get a little bit more dependent on the suffix of our word, so the ending of our word. So If it only has one atom in it, then we name it using the name of the element, except we change the ending. So oxygen would become oxide, sulfur becomes sulfide, and as we saw before, chlorine will become chloride. Okay, this IDE tells us that there is only one element in the anion and it is negatively charged. So if we look at sodium nitride, this is going to be sodium ions with nitrogen anions. And nitrogen is in group 15, so it will form -3 anions. Sodium is +1, so I will have to get 3 sodiums for every 1 nitrogen, swap and drop. Na3N would be the formula for sodium nitride. Things get a little bit more complicated when we come to polyatomic ions. Polyatomic ions are compounds, usually covalently bonded molecules, that have an overall charge to them. Okay, so they're groups of atoms that carry a charge when they're bonded together. They can be positively charged, such as the ammonium ion, or negatively charged, and they have specific endings when we talk about them, when we name them. The compound endings basically follow this. As we said, IDE is one element, it's only that element. ATE tells us that there is more than one element in it, and it's oxygen. Okay, so carbonate has carbon and oxygen. Okay, ITE is it's exactly the same as for 8, but it has one less oxygen. And if we look at this, we can see that the most oxygen is indicated by per, and then it might be chlorate, and then it might be chlorate, chlorite, and hypochlorite. We tend to, the only ones you need to memorize will be in the ATE and ITE suffix, so things like sulfate and sulfite. These will have a list that you need to memorize, and you'll be given a Quizlet link, which I will provide you in order to memorize. But if you have a look at this, we can look at an example where if we talk about sulfate, the anion, SO4 2-, this is sulfate. When we talk about sulfite, it will be one less oxygen than sulfate, so SO3, but the charge remains the same. So this will be sulfite. Okay, and we'll have lots of practice in doing these, but in year 11 you do need to memorize the table of ions that is provided in your textbook. So this periodic table here gives you an idea of the ions, and I will give you a physical copy of this in class. It also lists some of the polyatomic ions that are commonly found. We don't need to know all of these, but we do need to know permanganate, phosphate, sulfate, sulfite. We should also know ammonium and hydronium. We will get rid of this acetate one. We will call it ethanoate. That's actually an old name for acetate. The modern naming convention for this is ethanoate. We will need to know carbonate, chloride, chromate, and dichromate. The other ones you will tend to be given the formulas when you're using them. In this middle area here, we will look at nitrate and nitrite. We will look at also hydroxide. These hydrogen sulfite and hydrogen sulfide, etc., we can derive from our sulfate and sulfites, and we will talk about that a little bit later on. But that's it for me on naming ionic compounds and how we get the formulas for them. We will, of course, have a lot of practice of this because it is a key skill. So I encourage you to go to your textbook, have a look at those key questions and start to practice this skill. because it is certainly one that we need in order to be able to write balanced chemical equations in the future. So I hope you have understood this, and I'll see you in class.